Hello students, thank you for watching and welcome to the lecture on chapter 5, which is about simple linear regression and correlation. Let us start with defining simple linear regression and correlation. Linear regression and correlation is a statistical tools used to measure the relationships among two or more variables. When we are measuring the relationships among two variables, the analysis is considered to be simple correlation and simple linear regression analysis. On the other hand, when two greater than or more than two variables are involved, simple regression and partial correlation is used. Therefore, in simple linear regression analysis and correlation, we study and we measure, we investigate the relationship among two variables. Regression analysis is a statistical technique that can be used to develop a mathematical formula or equation showing how variables are related. On the other hand, correlation analysis deals with the measurement of the closeness of the relationship which are described by the regression equation or regression formula. So that we say that there is correlation if the two series of items vary together either directly or indirectly or inversely, so that we only find correlation between two variables only when there is direct or indirect relationship among the two variables. Simple correlation is, it is the measurement of the relationship or the closeness of the relationship among between two variables. Let us suppose that our two variables are named x and y, and there are different values of x variable like x1, x2 up to xn, and if we assume different values for y variable like y1, y2 and y up to yn, therefore when the higher values of x are associated with the higher values of y, and the lower values of x are associated with the lower values of y, so that we can say there is either positive or direct correlation between x and y, so that when the value of x increases, by the same fashion, if the value of y also increase, therefore we say that x and y have positive or direct correlation. For example, income and expenditure have a positive or direct correlation. The same is true for the number of hours students spend in studying and the scores that they will obtain from the exam. At the same time, height and weight have also positive or direct relationships, and distance covered and the fuel consumed by a car are also determined to have a positive or direct relationship. On the other hand, when the higher values of x variable are associated with the lower values of y, and the lower values of x variable are associated with the higher values of y variable, then x and y will have a negative or inverse or indirect correlation, so that a negative or inverse correlation between x and y is there when the higher value of x are associated with the lower values of y, and when the lower values of x variable are associated with the higher values of y variable. The best example for this negative correlation between x and y or between variables are like the relationship or correlation between demand and the supply, and the correlation between income and the proportion of income spent on food is also determined to be a negative or inverse correlation. So that correlation between two variables may be either direct or indirect, negative or positive, or it may be, direct or inverse. Let us proceed to how we can interpret the correlation between two variables. The correlation between x and y variable may be positive when the slope is between 0 and 1, or the correlation between two variables is perfect positive when the slope of the two, the equation is determined to be 1, and when the slope of the equation is 0, we determine that there is no correlation between the two variables. And when the slope is between -1 and 0, the correlation between two variables is determined to be negative. And when the slope of the equation of x and y is determined to be -1, we can say x and y have a perfect negative correlation. The existence of correlation between two variables may be because of three reasons. The first reason for the correlation of two variables is one variable being the cause of the other, which means if one variable causes an effect on other variable, therefore there will be a correlation between these two variables, and this is one reason. And the cause is called subject or independent variable, a variable that is the cause of the other variable is known as independent variable, and the effect is called dependent variable. The second reason for the correlation between two variables is when both variables are being the result of a common cause, which means if the correlation that exists between two variables is because of their being related to some third force, so that if there is some other force that causes an effect on both variables, in the meantime we say that these two variables are correlated with each other. The final reason for the correlation between two variables is chance, which means the correlation that arises because of chance, which is usually known as spurious correlation. For example, the price of the nut server and the grade of students in USA may be correlated by chance. The same is true for the weight of individuals in Ethiopia and the income of individuals in Kenya. These two variables may be correlated only because of chance, so that there are three reasons for the existence or presence of correlation between two variables. The other concept that we need to know regarding correlation is correlation coefficient. Correlation coefficient is necessary if we want to see the existence of a likelihood of any relationship between variables we study. For example, in our case, if we assume two variables, x variable and y variable, therefore the correlation coefficient between x and y, which is denoted by r, is determined by this formula. R is equals to the sum of x times y minus n into x bar times y bar all over square root of the sum of x square minus n times x bar square times the sum of y square minus n times x bar square, where x bar is the mean of x variable and the y bar is the mean of y variable, and r is the correlation coefficient. So that the correlation coefficient between two variables is calculated or determined by using this formula. And when we look at the results of R, i.e. correlation coefficient, we find the result is between -1 and 1, and also R is symmetric. The result of R or correlation coefficient is interpreted as follows. R results may be interpreted as perfect positive relationship if R is 1, so that if at the end of our calculation we obtained a result of 1, that implies the correlation between the two variables is perfectly positive. Sometimes we may obtain a result between 0 and 1, and this implies some positive linear relationship among two variables. And when the R value is 0, it implies that the two variables have no linear relationships. And if R is between -1 and 0, it implies that the relationship among two variables is somewhat negative. And when we obtain our value of -1, it implies a perfect negative relationship between two variables. This is how we can interpret the different R values that shows the correlation between two variables. Let us deal with correlation coefficients by taking one example. Suppose that we are going to study the correlation between two variables, i.e. mid-semester exam or midterm exam and final exam. And for example, if we take 10 students as a sample, and if we gather midterm exam and the final semester exam results of these 10 students, and if we summarize this data in terms of table as follows, then we can start to examine the correlation between two variables x and y. Let us denote the midterm exam or mid-semester exam by x and the final semester exam by y. Therefore, in this case, n or sample size is 10. We are looking at midterm and the final exam results of 10 students, hence n is 10. And when we calculate the mean of midterm exam results of 10 students, which I mean to say x bar, we add midterm exam results of all of these 10 students and we divide the result by 10. Then we'll obtain x bar or the mean of mid-semester exam of 31.2. The same is true when we calculate the mean of final semester exam results, which means we add together the final semester exam results of 10 students, here this column, then we divide the result by 10, then we'll get 32.9, which is y bar, or the mean of the mean of final semester exam results of 10 students. And when we square x bar, i.e. 31.2 times 31.2, we'll get 973.4. And when we square x bar, i.e. 32.9 times 32.9, we'll get 1082.4. 4. Then when we calculate the sum of x times y, which means if we multiply the mid-semester exam result of each of these 10 students by their final semester exam results, and when we add the results of this multiplication, finally we will obtain a result of 10,331, and the sum of x squared is 9,920, which means if we try to here square mid-semester exam result of all 10 students, and when we add the results of these 10 students, we'll obtain this result. The same is true for the calculation of the sum of y squared. We squared the final semester exam result of all of these 10 students, here this column, then we add together the results of each row, therefore we'll get 11,003. These are the terms that we need to calculate before we get this expanded equation or formula of R. Therefore, let us substitute these results or figures in the correlation coefficient or R formula, which means R is equals to the sum of x, y, which is 10,331 here, minus n is 10 into x bar or the mean of mid-semester exam result, which is 31.2, times xy bar, which is 32.9, all over square root of the sum of x squared, which is 9,920, minus n, which is 10, into x squared or x bar squared, which is here 973.4, times in brackets the sum of y squared, which is 11,003, minus n, which is 10, into y bar square, which is here y bar square, which is 1,082.4. Then finally we will obtain 0.363. This is the correlation coefficient between x and y, which implies mid-semester exam and the final exam scores or results of a slightly positive correlation, as 0.363 is between positive 1 and 0. This is how we can determine the correlation coefficient between two variables, x and y. But sometimes our data may be qualitative, so that when we are dealing with the correlation coefficient of qualitative data, we need to work through 3 steps. Step number 1 is we begin by ranking the different items in x and y. Then we find the difference of the ranks in a pair, which is denoted by D. Then finally we use this formula, R sub S, which is coefficient of rank correlation, or Spearman's rank correlation coefficient, is equal to 1 minus 6 times the sum of D squared all over, over n to n squared minus 1. Therefore, when we are calculating the correlation coefficients on qualitative data like efficiency, honesty, intelligence, and other variables, we need to work through 3 steps. Let us deal with one illustration. Suppose that Steel and Almas were asked to rank 7 different types of lipsticks. And if we wanted to look at the correlation between the tests of the 2 ladies, Steel and Almas, and if the test results, or if Steel and Almas ranked these 7 different types of lipstick this manner, let us denote or represent the types of lipstick products as A, B, C, D, E, F, and G. And if as they ranked these 7 different types of lipstick this way to 1, 4, 3, 5, 7, 6, and if almost ranked these 7 different types of lipstick as 1, 3, 2, 4, 5, 6, and 7, therefore we can calculate the correlation between the tests of Aster and Almas by working through 3 steps as follows. The final formula that we will apply in order to compute the correlation coefficient of the tests of these 2 ladies is 1 minus 6 times the sum of d square over n into n square minus 1. So that in order to work through this formula, we need to first determine or identify the result of here n, or the value of n, the value of here n square, the value of d square, and the sum of even that's the term of d square. Here, if we represent the test result of Aster by x, and the rank is given by Almas by y, which is rank 2, done in this way by using 2 different columns. Therefore, the difference between the rank is given by x and y, or Aster and Almas, for 7 different types of lipsticks is calculated in this way. The difference between 2 and 1 is 1. Therefore, 1 minus 3 is negative 2. 4 minus 2 is 2. 3 minus 4 is negative 1. 5 minus 5 is 0. 7 minus 6 is positive 1. 6 minus 7 is negative 1. When we square the difference in ranks, or d, therefore 1 squared is 1, and negative 2 squared is 4, and we work in this manner. And finally, when we add together, or when we calculate the term of d square, we will obtain 12. Therefore, d squared is the sum of d squared is 12. Let us substitute these figures into r sub s. Therefore, r sub s is equals to 1 minus 6 into the sum of d square. Here is 11 over n is here 7, the number of lipstick products, in times n square is here, n is 7. 7 times 7 is 49. So that 49 minus 1 will be 48. And finally, we will get 0.786, which is r sub s, or which is the coefficient of rank correlation between the tests of the 2 ladies. And since 0.786 is a result between 0 and 1, it implies there is a positive correlation between the tests of these 2 ladies, i.e. Aster and Almas. This is how we can determine the correlation coefficients for, qualitative type of data. Let us get forward to simple linear regression. Simple linear regression is a statistical tool that helps us to measure the linear relationship between 2 variables. And we usually denote dependent variable by y and the independent variable by x. And a line fitted to the point that plotted the scatter graph, which describes the average relationship between the 2 variables, is known as a simple regression line. Therefore, if we wanted to see the type of relationship between x and y, it is advisable to prepare a scatter plot before fitting the model. And the linear regression model is stated this equation: y is equals to alpha plus beta times x plus e, where y is dependent variable, x is independent variable, alpha is regression constant, beta is regression slope, e is random distribution term. And when we wanted to estimate the above model, we can estimate by this equation. Y hat is equals to a plus b times x, where a is a constant which gives the value of y when x is 0, that is y-intercept, and b is a constant which indicates the slope of the regression line, and it gives the measure of the change in y for a 1 unit change in x. Therefore, it is also a regression coefficient of y on x. A and b are found by minimizing a squared sum of error, which is the sum of a squared, as the sum of y minus y hat square, where y is observed value and the y hat is estimated value, which is a plus b times x. And this method is known as OLS, or ordinary least square. When we minimize this one,